Okay, so we do change of basis. So we learned basis last time. So we have vectors in vector space. And then we call these vectors or bases. These vectors spans and linearly independent, right? So we called those vectors or bases, satisfy the two conditions, okay? All right, now coordinate vectors. Definition for coordinate of vector. Okay, so we have suppose the set B, fancy B, is a basis. We are using this notation. This is actually notation, basis. Is set of vector B1, B2 until BP is a basis for a subspace H for each X is in H, the coordinate of vector X, long name, relative to the basis B. Relative means respect are the coefficient, scalar, or some book indicate that weight, C sub 1, C sub 2, until C sub P, such that vector X, which is linear combination form, right? B1 plus C2, B2, CP, BP, B sub P. And the vector in RP. So we have coordinate of a vector X. We denote it this way. It's a fancy notation, right? And this will be only the coefficient, right? So C sub 1, C sub 2, CP, C sub P. So it's called coordinate of vector X, or we called relative to the basis B, or the B coordinate vector of X. Okay, so we call the three difference name. Coordinate of vector X related to the basis B, the B coordinate vector of x. I think this is best called v coordinate vector of x. All right. So let us do this. We have a basis, vector b1, vector b2 for R2, and vector b1, column vector, which is 1, 0, and vector b2 has 1, 2. And suppose the vector x is in R2 as well, has the coordinate vector so this coordinate vector x, we denote it this way, right? Equal to -2 and 3. Find the vector x. Okay, so let's take a look the definition. So this one be coordinate of a vector x, right? Then they give you us they give us only scalars, right? Coefficient. Coefficient means only the number in front of that vector, right? So in general, the number in front of a variable, right? In that case, it's in front of vectors. All right. Now, that is b coordinate of a vector x. Yeah, that is that. Okay, then how do we find x? We just read it as a linear combination, right? Okay, so we have x bar. Okay, so there will be c sub 1, b sub 1 plus c sub 2, b sub 2, right? Okay, so there will be c sub 1, c sub 2. Yeah, so that is -2 b sub 1, which is 1, 0, plus c sub 2, which is 3, and 1, 2. So that is, we have -2 plus 3 and 0 plus 6. So we get 1 and 6. Okay. Thank you, the wrong message. Let me arrange a little bit. Okay, now we have the vector x, which is 1 and 6. Maybe I want to make separate, but then it's related. Or the coordinate of x related to the standard basis. So we have a standard basis, right? So e sub 1, e sub 2, right? So there we go. So we have this notation we're using, read in Greek. Epsilon. 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 Like that. Can you please, Alan, can you please find out the spell? Epsilon, epsilon. Epsilon. Oh, hold on 1 second.
I think the first O is actually
Epsilon. Thank you, Weasley. Thank you, Alan. Epsilon. Yeah. Joe, what? Oops. All right, so this will be, so we have a set of standard basis, which is E sub 1 and E sub 2. Okay, find, we want to find this time B coordinate. Oh, this is not B, this is epsilon coordinate of a vector, right? So we denote this way. Okay. All right. Then we knew that this is the vector. So we can express as a linear combination, right? So in that case, we have 1, 6 equal to E1, E sub 1, which is 1, 0, and E sub 2, which is 0, 1, right? Okay, now, yeah, I knew. Hold on 1 second, I'm not done yet. Okay, then from this one, we have to make 1 and 6, right? So what kind of scalar coefficient we need there?
well, for the first, for 1, 1, 0, it'd be a 1.
Yeah, 1 and 6,
and
right?
6, yeah.
Good job, thank you. So there will be so this will be equal to 1 E sub 1 plus 6 E sub 2. So look, this is the same as this, right? So we can say that this so we can say that thus epsilon coordinate of a vector x is the same as vector x. Okay. All right. Now, let us do one more. Let V1 equal to 362. B2 equal to -101. We have x equal to 312, 7. Okay, we have a basis, which is V1, V2. Then P is basis for H equal to span. They just describe the definition of a basis because V1 and V2 are linearly independent. Now you can check that linearly independent, right? Determine if the vector x is in H, and if it find the coordinate, they should make a short vector of x relative to basis B. Okay, so this means find this. Yeah. So they express it as an English like that. Okay. So basically we are looking for scalar coefficient in linear combination form, right? Okay. So think C sub 1, B sub 1 plus C sub 2, B sub 2, right? Okay, now X is given, B sub 1 is given, B sub 2 is given, right? So we want to find C sub 1, C sub 2, right? So B coordinate, C sub 1, C sub 2, like that, right? Okay, now X, which is, let me just copy. And B1, C sub 1 plus C sub 2, negative 1, 0, 1. Okay, now we have, so augmented matrix 3, negative 1, 6, 0, 2, 1, 3, 12, 7, right? Okay, now reduce the row echelon form. So Alan gives us 1, 0, 2, 0, 1, 3, 0, 0, 0. This means so we had a solution before, right? X sub 1, X sub 2. In that case, it's C sub 1, C sub 2, right? So we have C sub 1 equal to 2, C sub 2 equal to 3, right? Okay, so we have answer. So the coordinate of a vector x, which is C sub 1, C sub 2, which is 2 and 3. Then we check the right, check it out. So we have 3, okay, so how about this? Check everything like this. Okay. Two, 3. Yep. You check. You check that, Alan. Okay. We got that? 3, yeah, very good. He checked that. Good job. Okay, now, I'm not good in drawing, but it took a lot of time. Make me drawing this one. It takes a lot of time. Oh, so bad. Okay, so basically, the scale is different. So this is the 3b1 with a vector plus a v2. So this is a v2. So 1 unit, v2. Then x is there. Yeah, it's supposed to be, looks like a parallelogram, looks like that. Yeah. And this is, it's hard to see, right? This is C. Thank you very much. This is the C basis vectors, basically, right? Okay, so this one, I label C1 there. It's hard to see. C2, I mean, sorry, 2C2, 2C3, 2, 3, 4, 5, 6. Yeah, like that. I'm sorry. Oh, yeah. 2C1, 3C1, 4C1, 5C1. Yeah. That's how we will label. Yeah. Okay. Now from here, 1 unit C2, 2C2. This is a 3C2 and 4C2. So we can add 2 vectors, right? Parallelogram, diagonally, right? Okay. So that is the one. So we say that we are using just the scalar, the coefficient for the, we had B, which is base B, right? So B coordinate of a vector X, right? So we read this one, C coordinate, C coordinate vector of X, yeah. So we are using just a coefficient scalar 6, 4, right? Here we are using just coefficient, which is 3 and 1, right? But look, the point is, even though this is the C coordinate, this is the base B coordinate, they have the same. Yeah, even though C and B and number is different, they have the same position, same spot. Can you see that? Okay, if they have the same spot, right? So we can change the basis easily, right? Okay, so we're gonna learn that how to change the basis, all right? Theorem 15. Let basis be B sub 1, B sub 2, B sub n, and basis C, little bit fancy one, like that. Like a curly. I cannot make a fancy. Okay, C sub 1, C sub 2, C sub n, B, basis of a vector space V, then there is a unique n by n matrix P. Okay, we denote this way. So this means change of coordinate matrix from B to C. Okay, such that, okay, let me continue the black one, such that we have a time. So C coordinate of vectors X is equal to change of coordinate matrix from B to C, and B coordinate from B coordinate of vector X. Long name. So let me denote the column of change of coordinate matrix from B to C, or C coordinate vectors in basis B. So we denote this one, which is matrix column vector, this way, B2, B sub 2, C coordinate, and B sub n, and base C, right? Okay, now we have another one, another definition. So since P and C is a square matrix, so it must be invertible. So not square, then we cannot have invertible. I showed you earlier, right? Invertible. Okay, then we can use this one. The notation inverse of the change of coordinate from B to C, and we multiply coordinate of C coordinate of vector X is the same as B coordinate of vector X, right? So this is the same as equivalent, imply equivalent. So this is the same as like this. So we are using change what? Let me see. What do you say? Okay, let me talk later in the chat. So we have a change of coordinate from the B to C. So we have an inverse of that. And this is the same as change of coordinate from C to B. Okay, so we talk about the basis, right? So we knew that this means from C to B. Okay, let us do this. Let B1 equal to -9, 1. B2 equal to -5, -1. and C1 equal to 1, negative 4, and C2 equal to 3, negative 5. And consider basis for R2 given by basis B of vector B sub 1, B sub 2, and C equal to C sub 1, C sub 2. Okay, let us do that. Find the change of coordinate matrix from B to C. Okay, so let me give you a quick way. So B to C, so we are making the vectors B here, C here, right? So B1, B2, B to C. Okay, so that is C sub 1, C sub 2, B sub 1, B sub 2. So C sub 1, negative 4, C sub 2, 3, negative 5, B sub 1, I can move, negative 9, 1, negative 5, negative 1, right? Okay, now, can you please to reduce the row echelon form? Give it to me. Thank you. Direct message. So we get 1, 0, 0, 1 there. And 6, 4, negative 5, and negative 3. So we are using change of coordinate. Coordinate from B to C, that is B sub 1, base C, and that. So there will be 6, negative 5, 4, negative 3. Okay, how about C to B? Let B1 equal to 1, negative 3, and B2, B sub 2 equal to negative 2 and 4, and C sub 1 equal to negative 7, 9, C sub 2 equal to negative 5, 7, and consider the base for R2 given by basis B, which is B sub 1, B sub 2, and C equal to C sub 1, C sub 2. We have a C sub 2. Find the change of coordinate matrix from C to B. Okay, so C to B, So C to B, we arrange this way. C sub 1, C sub 2, and B sub 1, B sub 2, right? Okay, so there will be 1, -3, B sub 1, B sub 2, -2, 4, C sub 1, which is -7, 9, C sub 2, -5, 7. Okay, can you please, yeah. Can you please give it to me? Reduce the row echelon form. Thank you. To run message. Okay, so we have 1, 0, 0, 1. So 5, 3, 6, 4. So we have a change of coordinate system from C to B, right? In the case. So we have matrix 5, 3, 6, 4. Excellent. Thank you for confirming. Okay, how about B to C? Let us using inverse. Find the change of coordinate matrix from B to C. Okay, we could use B to C, right? How about we are using the inverse notation? So we had inverse notation of B to C, so C to B, right? And then inverse to get we can find the matrix change of coordinate from B to C. Yeah. Okay, so then we have this one, right? Can you please give it to me inverse of that? So we get inverse. Thank you. The message. So we have a +2, -3, -3 over 2, +5 over 2. Okay. So we are done for today's lecture. Thank you for coming. Have a nice evening. I'll see you tomorrow. Thank you.